study that for the lash. And I said, no. I was like, it's 20% of my grade. If you want me to study that much, then you need to make it a separate grade or something, because that's not cool.
I agree with that.
And then she's like, well, life's not fair. And I'm like, yeah, that's true. Life's not fair, but sometimes life's not fair and you can't do anything about it, but sometimes you can. You know? I was just not very happy that day.
And apparently you're very shy.
Oh, totally. I'm so shy.
Okay. I'm hoping that you guys all watched the lecture that I posted.
Yeah.
I looked for it. I didn't.
What? It's right.
I read the first part of the chapter.
It's right there under the respiratory system notes. That's where I put all the lecture, all the.
Are you gonna finish the last page?
I'm gonna finish the whole thing.
You have to?
I'm gonna finish the whole urinary system today.
Oh, I'm in the last page of
Oh, you actually need help on that last page?
Oh, do I?
No. But. Yep. So all we had to do on the last page was that little thing here. Right here. We did it. Okay. Okay. We did it. Okay, so we're going to start on respiratory system, but not until after we finish urinary system. Urinary system's not too bad to do today. You just have to stick with me, and I got to start you out in one important place. And then I'll do just a teeny bit of review over the stuff that I talked about. First off, the most important thing to understand about the urinary system is that you have to understand what is meant by these three terms. So when you are doing processing the blood plasma to end up making urine and basically cleaning the blood, you are going to be doing 3 steps. And the 3 steps are all exchanging fluid between blood tubes and pee tubes, which is the not so fancy way of saying between the uriniferous tubule and the peritubular capillaries. So this is the figure from your anatomy book, because your physiology book doesn't show the nephron very well. Basically, every place that you have blood tubes next to pee tubes, you can do exchange between them, right? It's lots of surface area. There's 1 million nephrons per kidney. And you have exchange between them. And so what we're going to have here is we're going to have 2 fluids with the potential for exchange between them. Oh, wait, I want this to be blood. We're going to have the blood, and we're going to have the urine. And in the lecture, I told you that they call it filtrate until it hits the collecting duct. I'm just going to call it urine, because eventually it's going to be urine. And they are highly porous and really close to one another. So you have the opportunity for exchange. As a matter of fact, there's almost never any connective tissue between the 2 tubes. There's just a little bit of interstitial fluid and sometimes basement membrane between them. So we're going to have 3 processes that we do. This is the blood that would be coming in from the renal artery, right? And this is going to be the blood that would be leaving via the renal vein. Can you agree that it's going to be different in composition and in volume?
Yes.
Yes? Okay, good. The urine it's a closed-end system. The first place, remember, anatomically, where you get anything that will later become urine is what? Any know? It's what anatomical structure? Glomerular capsule, the capsule, right? Okay, so this is closed-end. Yes? Are you with me? So this is not open-ended. It's not like you've got urine going all the way through your body. It's closed-end. And then anything that you do not retain in the blood would end up in the toilet, right? Okay? I'm going to say pee like a whole bunch of times today. Sorry. All right. So it's not going to get much worse than that. Okay. So there is a 3-step process for processing the blood plasma. And the first step is filtration. And filtration is pressure driven, so it moves things from where to where? Yeah. And which fluid to which fluid? Blood to urine. Okay, what kinds of things move out? Filtration is not selective, so it's going to move anything that fits through the holes and a whole bunch of water. So you move boatloads of water. Either 47 gallons or I think it's 180 liters or so per day. But you definitely don't pee that much, so you know you gotta bring a whole bunch of it back in. What else do you move? Ions, a whole bunch of them, because they're small enough to fit through the holes. nutrients,
Waste.
yeah, including glucose and amino acids, a bunch of other stuff, and then wastes. Okay? And then this is a really general getting rid of stuff mechanism. I always use the analogy with the urinary system is that cleansing blood is kind of like hoarders. So if you had a house that was so completely trashed and full of trash that you didn't even know where to start, maybe a good place to start would be to take everything out of the house and dump it on the lawn so that you could look to see whether any of that stuff was necessary to come back to the house. And filtration does that. It just sort of generally dumps everything that will fit through the door out on the lawn. Does that make sense? But then what you're going to do is take a critical eye and you're going to look at what's on the lawn and see what is worth bringing back in. And that's the second step, which is reabsorption. Reabsorption. And it moves stuff from the urine back into the bloodstream. And you're selective about what you're doing. And as a matter of fact, we can put a little bit of anatomy together with this because remember way back in anatomy when you learned that the kidney tubules were simple cuboidal epithelium? These are the selector cells. They have channels and carriers on them that decide what to reabsorb. Does that make sense? Okay? So reabsorption. What do you reabsorb? Well, you reabsorb a whole bunch of water. If you filter out 180 liters, you reabsorb about 179 of it. So you only pee about 1 liter to maybe 2 liters on a day. And then you reabsorb. How many of the nutrients would you try to reabsorb? All of them, and sometimes you're successful. And you don't generally reabsorb any waste products with the exception of sometimes you will reabsorb urea because it helps to maintain your blood pH. So if it's necessary, you will reabsorb it. Most waste products you don't reabsorb. And then ions, you will reabsorb a whole bunch of ions, okay? And we'll talk about whether you can control that reabsorption or not. Water, nutrients, and ions. And then, so this is all the stuff that we decided to bring back into the house. But now, we go through the house one more time and we take a critical look at what's in all the cabinets and we decide, do we really need 470 cans of corn? Really? Right? Zombie apocalypse, maybe. But, you know, I've got my mother-in-law's house staked out for the zombie apocalypse. She's got food storage. So you look at the house and figure out what you need to get rid of, and you take a critical look. And again, it's these cells that are going to decide what to move, only this time they're going to be moving in this direction. And that third stage is secretion. And when you secrete stuff, it ends up in the urine. And this is mostly wastes and excesses. Does that make sense to you? Wastes and excesses, like anything. If I had too much calcium, I'd secrete calcium. If I didn't have enough, I wouldn't secrete it, right? So wastes and excesses. And so what's going to end up in the urine is a whole bunch of water, because you can't do it without water. Excesses, wastes, and hopefully no nutrients, if we can. And what's going to end up with the blood is going to be two things, lower volume and a more ideal composition, right? When it leaves the kidneys. Definitely going to be lower volume. It should be what?
Well, the tonicity will be changed too.
Yeah, it should be more isotonic because you try to maintain the extracellular fluid, the blood plasma, with the proper tonicity. That's what you're trying to do.
Is that how it
Okay.
decides, or why it decides how much water to bring back?
Yep, it is. Mm-hmm.
Maintain pH.
Mm-hmm. So, right, okay with the big picture? So, the most useful thing that you can do for your studying with the urinary system is to be able to use these terms very, very effectively. Because, for instance, when we get going, I'll start to talk about sodium filtration. But then I will also talk about sodium reabsorption. And those two questions both use sodium, but they mean something totally different. And you do it at a different place in the kidney. And one of them is under hormonal control, and the other one is those kinds of things, okay? So you got to be able to figure that out. And for instance, we will do potassium filtration and potassium reabsorption and potassium secretion. And they'll be different, okay? So when I took a urinary test, this is the first thing I wrote down. I'm like, okay, which direction are things going? Because it's hard for me. Maybe it's just because I'm spatially challenged. I'm a little bit of a spatial, I'm slow spatially. Okay, so what we did in the lecture that I posted for you was really talk about this one, which is filtration, which is pressure driven. And you guys remind me Filtration happens from where to where? Anatomical structures. From what anatomical structure into what anatomical structure? Glomerulus into glomerular capsule or Bowman's capsule, right? Okay, that's where filtration occurs. And since it's pressure driven, it's really, really sensitive to pressure changes, blood pressure changes, yes? Okay, so just a couple of things, and one of the things is that the general rule is that anything that increases systemic blood pressure increases filtration, and the way that we refer to filtration is GFR, glomerular filtration rate. Is that okay? So generally, anything that increases systemic blood pressure increases GFR, with the exception of one hormone/neurotransmitter that increases systemic blood pressure but decreases GFR. Anybody remember what that was? Epinephrine. It's epinephrine. Epinephrine increases systemic blood pressure by mechanisms that we've understood already, right? But it ends up decreasing GFR because it causes constriction of the afferent and the efferent arteriole. Does that make sense? Okay. So the note said that basically, for that reason, if you have somebody who has low blood pressure is going into shock, but they have kidney failure, you would not use epi. Does that make sense? You could use dopamine, and there's other ways to treat it as well, but you definitely don't use epi. Go ahead.
So maybe this ties in, I don't know, I'm just thinking, so you know when you go to the dentist and you get a numbing shot, you're having a procedure and it has norepinephrine in it,
Mm-hmm.
you typically have to pee a lot within a short amount of time. So why is
Oh.
that? It's because it constricts your heart faster, and so it filtrates it faster or something?
Do you have to pee when you get a shot?
Well, it's happened to me, but I've been doing like hours.
Oh.
And so I've been watching it, and most patients, like if they, get numbed up or whatever, a lot of them are like, after like an hour, they're like, I didn't really have to eat. And I thought, well, that's happened to me too. So
It also could just be, increased blood pressure because you're nervous. I don't know if it's the norepi that they give you. I have no idea.
it is. I asked him what it was. It was norepinephrine. So I'm like, what is this? Because your heartbeat's faster.
Ask them. You're going in dental hygiene. Ask them why. Like, why do I have to pee? Because that's really inconvenient. Because you got like stuff and yeah. Okay. So the only other thing that I want to talk about that I actually did on the lecture is just to remind you of. So I was just talking about systemic regulation of blood pressure equals regulation of GFR most of the time, with the exception of the sympathetic nervous system. But then when we talk about local or auto-regulation of GFR, autoregulation, remember that there are two ways that you do autoregulation of GFR, and that is, where's the first one? Myogenic regulation of GFR, and this is just paracrine agents, remember? If the afferent arteriole, just the afferent arteriole, detects high pressure, and this is local, right, not systemic, so we're not doing systemic regulation right now. It's just like a tweak in pressure by like changing body positions or something. What does it do to protect the capillary bed? It vasoconstricts to decrease flow to it, right, to protect the capillary bed. So that's called myogenic regulation. And then tubuloglomerular feedback was the one that was a little hard to understand. This is still is paracrine. What happens is if you detect this time a lot of flow going by the distal convoluted tubule. Where's that picture? Damn you, where are you? A lot of flow going by the distal convoluted tubule, it can feed back to the afferent arteriole. So if the distal convoluted tubule has lots and lots of urine in it, yes, it feeds back to tell the afferent arteriole to do what? Yeah, vasoconstrict, right? It says I've got plenty of pee. Settle down. That makes sense? So this is local. That's just local regulation of the kidney. Just so you know, those little tweak mechanisms aren't very powerful. They'll work just a teeny bit. But if the systemic actually contradicts what the local does, the systemic will win. These are just little tweaks that help you like maintain your GFR, different body positions, different urine formation. Okay, so the second phase that we're going to do now is tubular reabsorption. And so when we're doing reabsorption, we're reabsorbing from the tube back into the blood plasma, okay? This is selective, meaning that these cells generally have transport mechanisms on them for anything that I want to reabsorb. And how do they decide how they will reabsorb it? Same way that we did way back at the beginning of the semester. Cheapest, fastest way first. If you can get it through simple diffusion, you do that. If you can't, you use a channel. If that doesn't work, you use a carrier. And if that doesn't work, you use active transport, right? Secondary before primary. That makes sense? So that's how we will do reabsorption. So reabsorption moves substances from what fluid back to what fluid? From the urine back into the blood. Yes, okay, good. So your normal GFR rate is around 180 liters per day, but you reabsorb about 178 to 179 of that. So that is a lot of reabsorption. So if you look at this table, you don't have to memorize the table. I just want to show you the approximate amounts. Water, you filter out 180 and you reabsorb 99.2% of that. Glucose, you try to reabsorb 100%. Urea, you sometimes reabsorb 50%. It helps maintain your blood pH. Potassium is the one that you lose the most, and we will see why today. And most of the other ones, 98, 99% of it is actually reabsorbed. So reabsorption is a very, very active process, super important. Okay, so basically what we are going to do, just to remind you that this is just going to be an example of that transepithelial transport that we learned before. Remember with transepithelial transport, you move something from the lumen across the apical surface through the intracellular fluid across the basal surface, and then this is just going to be a basement membrane. This is, by the way, fenestrated, so reabsorption isn't usually much of a problem once you get it to the right place. Is that okay? Okay, so we learned all those transepithelial transport mechanisms at the beginning of the semester. This is just going to stick them in a specific location, okay? All right, so like I said, you will do reabsorption by the cheapest, fastest way that you can. Let's talk about reabsorption of some important stuff like glucose. Do you agree that glucose reabsorption is pretty damn important? Yes, glucose reabsorption is really important. Normally, under normal circumstances, you will reabsorb 100% of the glucose that you dumped. Right? So you go and look on the lawn, and then you find money on the lawn, and you're like, do we want to bring this back into the house? Yes. How much of it? All of it? Yes, exactly. Okay? So that's what we want to bring back into the house. And the reabsorption mechanism is one that you already know. You just didn't know that it goes on in the kidney. It is secondary active transport with sodium. Is that okay? So sodium's going to move in, and glucose is going to move in with it. Yes, and you are using sodium's concentration gradient to bring it in. That makes sense. And then let's just follow glucose for a second. By the way, what kind of protein is that? What kind of transport protein that will move glucose and sodium simultaneously? It's a carrier, right? Okay. And then we're going to follow glucose, and glucose will move out via another carrier because of its size. You don't need active transport right there. You don't need ATP because it's moving down its concentration gradient. Simply because whenever I get glucose in the bloodstream, I carry it away, right? Okay, and then of course you do the sodium-potassium pump at this side. Make sense? So this is just secondary active transport. This first part is facilitated diffusion with the hitchhiker, and then here you do straight facilitated diffusion, and then here you do the sodium-potassium pump. So that's how you do sodium reabsorption. And sodium reabsorption happens, you will pay for it if you need to, but usually you don't need to. But I will tell you that you only have so many sodium carriers to reabsorb. And so if it's Thanksgiving and there are 4 kinds of pie, and how many times are there 4 kinds of pie? Once or twice a year. How many kinds of pie do you eat? You eat all 4. The problem is that the filtration level for glucose doesn't change, right? You basically are still filtering it all out. But your reabsorption mechanism is subject to saturation limits, isn't it? Does that make sense? You only have so many glucose carriers. And if any of it gets into the collecting duct before you reabsorbed it, then you pee it out, right? So the capacity of the glucose reabsorption carriers is limited, which means that under normal levels of sugar consumption, glucose consumption, you will reabsorb 100% of it. But after Halloween, or if you're a diabetic, or after Thanksgiving, you're probably going to have sweet pea, right? Yeah. And if you're like me, I will eat all of the fresh homemade whipped cream all the time on all the things. So good. I don't even know why anybody buys whipped cream in a can. Isn't that the easiest thing to make? Well, is like the best, easiest thing to make well. I'm like, why the hell did you buy it in a can? It takes like 2 minutes to make it. Okay, so glucose reabsorption, normally 100% is reabsorbed. If the glucose gets into the collecting duct, it will exert an osmotic effect on the water, right, in the interstitial fluid around it. And so it ends up basically pulling fluid into the tube. And then you will have sweet pee, that's called glycosuria, right? And lots of it, that's called polyuria. Does that make sense? It's just because of the osmotic effect of glucose going through the tube. Good? Amino acids are reabsorbed in this mechanism as well, and some other things that you actually need. Water-soluble vitamins, some of those are reabsorbed by that mechanism. So basically, under normal circumstances, 100% reabsorption of glucose by secondary active transport. That's what you normally get. Okay, with sodium ion reabsorption, we have 2 steps reabsorption. Okay, and this is where you need to stick with me. Sodium is generally actively reabsorbed, which means a lot of times you will pay for it if you have to. That's simply because by filtration, you moved a whole bunch of sodium out, but you didn't move it out disproportionately. You still got a whole lot of sodium in here. So when you try to bring it back in, a lot of times you're moving it from high to high. And so a lot of times you will need to actively transport it. Luckily, there are active transport mechanisms here on the cells that you can use if you need to, okay? So it's actively transported through all parts of the tube, but I'm going to separate the transport into 2 steps. The first step is proximal convoluted tubule reabsorption of sodium, okay? PCT reabsorption of sodium. Did you go through the anatomy so that you're cool with this? Proximal convoluted?
Somewhat.
Yeah? Okay. I'll show you pictures just to kind of help you with the anatomy a little bit. Okay, so we just pushed it all out, and now this is the proximal convoluted tubule. I'm going to do reabsorption from the tube back into the bloodstream. Your anatomy textbook has a little bit better picture because you can see the blood tubes next to the P tubes, right? So I just pushed it into the P, and now I'm going to pull it back into the blood. Does that make sense? In the proximal convoluted tubule. So there's proximal convoluted tubule reabsorption of sodium, and then there's distal convoluted tubule reabsorption of sodium, and they are different. Okay, one of them you can control, and one of them you can't control. What happens at the PCT, the proximal convoluted tubule, is what we call non-regulated reabsorption of sodium, or obligatory, if you know that word. It means you're obligated to do it, you have to do it, you don't have any control over it. Obligatory or non-regulated reabsorption of sodium. And the obligatory or non-regulated reabsorption of sodium is 65%. Of the stuff that you dumped out on the lawn, you will bring 65% of it back into the house, and you can't do a darn thing about it, okay? It does what it wants. It's basically like a teenager. You can tell it anything you want it to do, and it's still going to do the same damn thing. And then later on, what you're going to have to do is clean up the mess at the distal convoluted tubule. So the distal convoluted tubule will take care of what we call the regulated reabsorption of sodium. So most of your sodium, 65%, is reabsorbed at the proximal convoluted tubule. This is called non-regulated, and you cannot change it. Okay, it always does that. The PCT has no control over this quantity, and no hormones have any control over that quantity. Is that okay? No aldosterone, no ADH. They don't make any difference to that 65%. Okay, but some sodium ions are reabsorbed in the distal convoluted tubule depending on the body's needs. Okay, and the distal convoluted tubule can decide to reabsorb 0 of that 35%, right, that's still left out on the lawn, or all of that 35%, but usually somewhere in between, right? Does that make sense? So if we do the extremes, you'll be able to see, you know, like either absorb it or don't absorb it, but realize that you usually do somewhere in between that. Is that cool with you guys? Okay, so some of the sodium is reabsorbed in the distal convoluted tubule. The sodium reabsorption in the DCT is varied and is hormonally controlled, mostly. And the hormone that controls it is ANP, and aldosterone. Let's talk about ANP first. Remember that ANP is released in response to prolonged atrial wall stretching, and it affects the kidney. And what ANP does, just concentrate on what it does to the kidney. It decreases regulated sodium reabsorption at the DCT. Decreases reabsorption, right? Does that make sense? Because I said the pressure was too high. I don't want it higher. It also inhibits aldosterone release. So that's a double whammy. Does that make sense? Okay. So basically, if you release ANP, you are going to let that 35% go. Make sense? Let that 35% of sodium and therefore water go. Everybody okay with that? Okay. So it also does one other thing. So everybody okay with the reabsorption? So what does ANP do? It inhibits sodium reabsorption where? At the distal convoluted tubule. In addition, it also does something that is consistent to sodium filtration, because ANP actually dilates the afferent arteriole. And what does it do to sodium filtration, therefore, or filtration in general? More out, less back, right? And that's a pretty effective way of regulating your blood pressure. Does that make sense to you guys? So it actually hits a double whammy. Increases filtration, decreases reabsorption, primarily of sodium. Are we okay with that? Okay. All right, and then we will talk about what you do if you need to do reabsorption, right? So how do I say yes to that 35% reabsorption? Well, there's a bunch of different triggers that will trigger that reabsorption. The communicator is primarily aldosterone, but let's talk about this. The major stimuli that will increase regulated DCT reabsorption are a decrease in blood pressure or blood flow to the kidney would stimulate reabsorption. You with me so far? Yes, a decrease in blood pressure or blood flow to the kidney would stimulate that reabsorption. Yes, nod, okay. A decrease in blood volume, like if I bled out, I would want to reabsorb the sodium at the kidney. A decrease in cardiac output. This doesn't have anything to do with cardiac output, but the kidneys will help in the way they can. If your cardiac output goes down, they'll say, oh, okay, we still need blood flow. I'll do what I can and do reabsorption of sodium, right? Okay, or an increase in the sodium concentration of the filtrate. So these three are looking at the blood, 1, 2, 3, but this one is looking at the filtrate. You can also say, hey, there's too much sodium in the filtrate. Reabsorb some of it, okay? So you look at the blood, volume, composition, pressure, right? And then you look at the filtrate, primarily just composition. Is that okay? Okay. Now, you already know this mechanism. The juxtaglomerular apparatus is monitoring these things with the afferent arteriole, the juxtaglomerular cells in the afferent arteriole, and the macula densa cells in the distal convoluted tubule. And it's monitoring those stimuli. And when it detects these stimuli, it will secrete the enzyme renin. We've already learned about renin. Renin will convert angiotensin to angiotensin 1. And then if ACE is around, that gets converted to angiotensin 2. Just look at what angiotensin 2 does now, and ignore the blood vessel effect for just a second. And look at what it does to the kidneys. It will cause the adrenal cortex to release aldosterone, right? So the kidneys detect any of this stuff going on, they will cause the adrenal cortex to release aldosterone, and then aldosterone will cause sodium reabsorption at the DCT. Is that okay? Aldosterone causes sodium reabsorption at the DCT, okay? So also the collecting ducts, but I'm just sort of saying DCT, it's all the distal portion of the tube. So the result is that if you detect any of these things and you release renin and ultimately get aldosterone, then the result will be an increase of sodium ions and water, an increase of blood volume, and a wet of blood pressure. Increase of blood pressure. So you already knew that. All we did was stick it in this place, right? The reminder, which isn't particularly pertinent to the kidneys, is that at the same time, angiotensin 2 would be also vasoconstricting systemically. Yeah, causing vasoconstriction. The opposite, by the way, is also true. High blood pressure detected at those places and or high osmolarity of filtrate will decrease renin and therefore decrease aldosterone and therefore decrease the DCT reabsorption. Is that okay? Okay, so before we go any further, the way that you control PCT reabsorption of sodium is what? Proximal convoluted tubule. You don't, because it doesn't do a damn thing you tell it to anyway, right? The way that you control DCT reabsorption of sodium is primarily 2 hormones. One of them will decrease reabsorption at the DCT, and that is what? ANP, right? And the one that will increase reabsorption at the DCT is aldosterone. Good? Okay. But remember that aldosterone doesn't move anything by itself, right? Every time you reabsorb sodium, it will cost you another positive ion, either a potassium ion or an H+ ion that ends up going into the urine. So aldosterone causes sodium reabsorption, but it causes potassium and H+ secretion.
So in other words, the net effect is not changing pH at all. You're bringing in plus and you're letting out.
Well, it's not affecting the electrical gradient. pH, it can, yeah, electrical gradient, yes. So you swap a positive for a positive, yes. That makes sense? Okay, all right. So now let's talk about potassium ion reabsorption, okay? Potassium ion reabsorption is easy because you don't really have any control over it. At the PCT, after you dump potassium onto the lawn, you will reabsorb 90% at the PCT. That's the maximum that you ever reabsorb. You can lose more of it, remember, because you can secrete it. Does that make sense? So you do potassium filtration, right? You do potassium reabsorption at the PCT with 90%, and then you've got 90% over here, and you can still lose some in the presence of what hormone? Aldosterone. Yes. That makes sense? Okay. So at least 10% of potassium is always lost. That's why this figure that we looked at, or this table that we looked at, the average potassium that we end up reabsorbing is only about 86%. So you can go down from 90. You can't go up from 90. Does that make sense? So which one is more likely to be in short supply? Which electrolyte, potassium or sodium in your body? Potassium, yeah. Sodium, we've got a whole bunch of mechanisms. In addition, we eat tons of sodium. But potassium, you're always going to lose at least 10% of the potassium that you ingested and went through your bloodstream, which is kind of interesting. Okay. So chloride ion and bicarbonate ion, those negative ions, the cations, those negatively charged ions, you don't usually even have to do anything to get them reabsorbed, because I just reabsorbed boatloads of sodium and boatloads of potassium, and it creates an electrical gradient such that as soon as there is a way for them to get through channel, they will just follow the electrical gradient. Does that make sense? So you just create this enormous wave of positive electricity that will end up being followed by negative electricity. Eventually, I will not be sick and actually be smart again, but I don't know when it's going to happen. Okay, so we just talked about reabsorption of glucose, sodium, right, potassium, and negative ions, chloride and bicarbonate ions. And now let's talk about water reabsorption. Water reabsorption is 2 steps as well. Water reabsorption is PCT and then DCT and collecting duct. And it's a little complicated, but it's not too bad. Here's the deal. You know that solutes suck and sodium sucks most. And when water can, it will follow what sodium does, when it can, okay? And it always can in the PCT. In the PCT, the tube has leaky tight junctions. So if sodium goes through, then water will follow because it creates an osmotic gradient. Does that make sense? And that is just what kind of transport. When you move it through the cell membranes, it's just osmosis, right? And when you move it between the cell membranes, it's diffusion. But basically, it's not active, right? If water can follow, it will follow. Does that make sense? Yeah. But in the distal convoluted tubule, the tight junctions are super tight, okay? So water cannot always follow. Water reabsorption in the distal convoluted tubule is controlled, and I'll talk about how it's controlled in just a second. So as sodium ions are actively transported from the filtrate, urine, back into the tubular cells and then back into the blood, the osmotic pressure of the blood increases, and then water will follow. So basically, here's the deal. When you reabsorb 65% of the sodium at the PCT, 65% of the water follows it. Okay? So that's the 65%. That okay? Okay? In the DCT, it will follow it if it can't, but you need ADH for it to follow it. That's what you're going to need. So the reabsorption of the remaining 35% of the water is regulated reabsorption. So basically at the PCT, we had non-regulated sodium reabsorption, non-regulated water reabsorption. At the DCT, we have regulated sodium reabsorption and regulated water reabsorption. Is that okay? So the reabsorption of the remaining 35% of water can be regulated. It occurs in the DCT and the collecting duct. The cells of the DCT and the collecting duct, however, for this regulated reabsorption, must contain ADH. ADH allows the cells in the DCT to become porous to water. Otherwise, they are relatively closed to water reabsorption. They have tight junctions, and they do not have aquaporins that will allow for it to go through. You have to allow it. Okay, so ADH comes from where? Posterior pituitary. And you need ADH from the posterior pituitary for regulated reabsorption. So here's the deal. If your ADH is low, then water can't pass through the DCT even if sodium was going. It's just like, hey, I want to come, and it can't come. So you can have sodium ion reabsorption in the DCT with aldosterone, but if you don't have ADH, you cannot have water follow it. And believe it or not, you're going to get large amounts of diluted urine. You kept a whole bunch of the sodium, you just did not keep a whole bunch of the water. For example, diabetes insipidus. Remember learning about diabetes insipidus? It's an ADH, sometimes an ADH hyposecretion, but it's not an aldosterone hyposecretion. So you should be keeping as much of that 35% of that sodium that you needed, right, because of aldosterone, but you're going to pee out a whole bunch of fluid. That makes sense? Okay. So it causes polyuria, and that's diabetes insipidus, a low ADH causing polyuria. Good? Okay. What if ADH is high? If my ADH is high, then water reabsorption is high. It will follow sodium at the distal convoluted tubule. And then the final volume of urine is really concentrated and really small and usually really stinky and really yellow, right? Does that make sense? Okay, so what controls ADH release? Well, the brain controls ADH release because remember when the blood is going by the hypothalamus, you just assess the osmolarity or tonicity of the blood to decide whether to release ADH or not. Does that make sense? So if the water concentration is low, the blood plasma is slightly hypertonic, then you release ADH, and then it impacts the kidney, and you do water reabsorption, right? And it will also cause you to be thirsty, right? So you need to drink more water, and you need to pee less water. If the water concentration of the blood is high, slightly hypotonic, then it will go by and it'll say, hey, don't release any ADH. We don't need any more fluid. Keeps you from being thirsty and makes you pee. Good? That makes sense? Okay, what about reabsorption of lipid-soluble substances? Lipid-soluble substances do whatever they please. You can filter them out by pressure and they will move right back in down their concentration gradient if they want to. So the kidneys are really no good at all at clearing lipid-soluble substances or toxins from the body. The liver has to help with clearing lipid-soluble substances or toxins from the body. Is that good? So what about anything else? So all the stuff that we didn't talk about. If a substance is not lipid soluble and has no carrier or transport mechanism, then generally once you moved it out on the lawn, it stays there. Okay, like creatinine and some waste products, uric acid, ammonia, those things are staying out there. Okay, so the third phase is tubular secretion, and it's not too hard because reabsorption is actually, I think, the hardest part of it. So we just did the hardest part. Tubular secretion is taking one last critical look at what's in the house and deciding what you need to get rid of, okay? And this is selective, so I am selecting what things I want to get rid of. Basically, it's moving blood, stuff from blood into the filtrate, and the secretion mainly occurs later. So you did filtration of the glomerulus into the capsule, and then you do reabsorption and reabsorption at the proximal convoluted tubule and the distal, but secretion is mostly later, because you actually sort of had to have time to do filtration and reabsorption before you need to select what to secrete. Does that make sense? So it happens primarily at the DCT. A little bit at the collecting duct, but not very much because there's not blood vessels around it. So there's two major effects. Kidney control of pH and ridding the body of certain materials. So ammonium ions are actively secreted. Some breakdown of medicine, penicillin, phenobarbital. Urea and uric acid that was reabsorbed but now isn't helping the pH. You can take another look at it and get rid of it. And then, of course, you get rid of, if I had any excess potassium under the influence of aldosterone, I would do potassium secretion, yes? That makes sense? Okay. So potassium secretion happens because of aldosterone. Sodium reabsorption happens because of aldosterone. And aldosterone comes from where? You know. The renal cortex. And, of course, it's exchanged for sodium. Does that make sense? Okay, so the main kidney control over blood pH is with deciding what to do with your H+ ions. So the kidney can dramatically impact blood pH by deciding how many H+ ions to hold on to versus get rid of. Is that concept okay with you? And then in addition, it can also decide how much buffer. The HCO3-, the bicarbonate ion, is a buffer, and it can decide to hold on or get rid of that. Is that okay conceptually? And by doing those things, the kidney has a tremendous impact on your blood pH. The kidney and the lungs are actually the two primary regulators of your blood pH. You can decide how much carbon dioxide to blow off, right? And in addition, you can also decide how much H+ and HCO3- to hold on to at the kidneys. Okay? Okay, so the kidney actively decides how much H plus to secrete, but then it also forces this reaction. So it can deal with the H plus that just goes by it and decide how much to secrete, primarily under the influence of aldosterone, but there's some other mechanisms as well. But it doesn't even just have to deal with the H plus that comes to it. It can force this reaction and then dump some excess H plus and hold on to excess HCO3 minus. So inside these cells right here, you can force this reaction. Take carbon dioxide, force it into H plus and HCO3 minus, and then decide what to do with each one of those. And when you do that, you can massively impact the blood pH. Does that make sense? Okay. So the H plus will be actively secreted if you were low pH, right? Actively held on to if you were high pH, right? And the HCO3 minus is reabsorbed or not reabsorbed depending on what you need.
And what triggers is deciding which to hold on to or not?
It's actually the pH that is impacted, and also aldosterone triggers it as well. But we'll come back to that with the respiratory system because it works in concert with these guys too. Okay, so the low blood pH that came to the kidneys could have been because of H plus ions. It could have been because of lactic acid. It could have been because of carbon dioxide. It could have been because you've been drinking too many sodas. It doesn't matter where it came from. This is the mechanism that it uses to help, right? It doesn't have to be because of carbon dioxide for you to help with it. Is that okay? Okay, so the low pH stimulates the tubule cells to secrete H plus. It is the low pH that they detect that will stimulate them to secrete H plus into the urine. Okay, so now we're going to summarize. In the proximal convoluted tubule first, and then we'll do the summary. So in the proximal convoluted, so we already know filtration is non-selective. And then in the PCT, in the PCT, we're talking about reabsorption here. That's why I'm writing it on this side. In the PCT, I will reabsorb what things? Glucose, how much? 100% if I can. Limited by the carrier capacity, right? Sodium, how much? PCT? 65% under any hormonal regulation? No, not in the PCT. You guys with me? Okay. Potassium, how much? 90% under any hormonal regulation? Nope. And water, how much? 65% any hormonal regulation? No. Okay. So that's PCT reabsorption. Okay. DCT reabsorption. Glucose, probably already did it. Don't have to worry about DCT reabsorption of glucose. Sodium, 0 to 35% under the influence of two hormones. Aldosterone increases, ANP decreases. Got it? And do I do any regulated reabsorption of, oh, this is sodium. Do I do any regulated reabsorption of potassium? No, can't do a damn thing about it. Just lose 90% at least. Do I do any regulated reabsorption of water? 0 to 35% under the influence of what hormone? ADH. Is that okay? Okay, so now let's look at the summary, and then I have a summary of the summary. So it gets easier, promise. It just takes me it takes me a minute. Can you kind of see how I study when you look at this stuff? I'm like, wait a minute, where's the big picture? I can't see it. Okay, so to summarize, in the distal convoluted tubule, when aldosterone and ADH are present, okay, the following occurs. Sodium is reabsorbed from the filtrate into the tubular cells, into the blood. But the movement of the positively charged ions must be balanced. So water will follow sodium as long as ADH is present. So in order to balance that massive reabsorption of all of those positive ions, generally also you have a reabsorption of the negative ions, and that is HCO3 minus. You don't control it though, it just moves with the sodium. And chloride. So those are reabsorbed as well. They're reabsorbed all along the tube, but you don't usually have to worry about them. Okay. So chloride and or HCO3 minus accompany some of the sodium moving into the tubular cells. But everything that you don't balance with a negative, you must flip for a positive so that I maintain the electrical gradient. So if the negative didn't follow it, then I would flip-flop it, like with aldosterone, absorb sodium, get rid of potassium, absorb sodium, get rid of H+. Okay? So the rest of the sodium moving in is balanced by other positive ions moving out into the tubules. And so the primary things that you are secreting over here, secretion, DCT secretion of potassium under the influence of what hormone? Aldosterone. And H plus under the influence of aldosterone as well. H plus secretion, there's more than one way to do it. You can influence it with aldosterone, and it alone can also just trigger its own secretion. Is that okay?
And your waste excess what?
Wastes and excesses of anything. Oh, that says DCT. This is just DCT secretion. That's where it's occurring. Is that okay? All right, so a summary of a summary. The summary of the summary is in the DCT in the collecting duct, so we already know what's going on in the PCT. In the DCT in the collecting duct, this is what happens. Assuming you have ADH and aldosterone, think about this. You are reabsorbing sodium, water, also chloride and HCO3 minus, yes, reabsorbing all of those. And you are getting rid of potassium and H plus, assuming that you have ADH and aldosterone. Yes? Okay, so there's a summary of a summary. It's not that bad.
So you're doing the chloride in the DCT as well as the PCT?
The chloride happens all along the tube.
But that happens as well in the DCT too?
You can't control it.
Okay.
Yeah, if you move sodium with the DCT, then chloride will move with it. It's just
Okay.
like an electrical gradient. There really isn't much of a barrier for all of the negative ion reabsorption. So as soon as you have positive ions moving by any mechanism, they'll just follow. Is that okay? Okay. So I very commonly write on quizzes and tests, like give you a list of hormones, ADH, aldosterone, ANP, EPO. I'll just throw some extra ones in there. Which one of these controls PCT reabsorption of sodium? None. Yes, there is no control of PCT control of reabsorption of sodium. Go ahead. Oh, there's two triggers. H plus secretion is kind of complicated. One, if aldosterone is around, you can either use H plus or K plus to get rid of, to balance out the positives. But then in addition, there's also just when the kidneys detect high H plus concentration at the blood, it will cause H plus secretion. So it's just a little feedback mechanism there. It's a pH control mechanism, yeah. So there's a couple of different ways. There's actually 2 more ways of doing it, but that's enough to start with, right? I mean, do you really want this to get more complicated? Do you want it to get more complicated? By the way, it simplifies once you sit and stare at it for a little while. It will simplify, I promise. Go ahead.
So that side right there has to do with reabsorption.
This is reabsorption, yes, because that's where we ended up with reabsorption. That is PCT reabsorption, and that is DCT reabsorption. These guys, by the way, are reabsorbed wherever the hell they want to be reabsorbed. PCT and DCT.
It basically follows sodium.
It just follows sodium. And if sodium is moving the DCT, it follows it there. If it's not, it doesn't follow it there. It just does whatever sodium and potassium do. Is that okay? And this business right here is secretion. Okay? Okay, so by the time you're done, you should have pee with water, excesses, and wastes in it, right? And you should have way fewer excesses, lower volume, and a disproportionate amount of good stuff in it. So the fluid that's coming, the blood plasma that's going in the renal artery is different than the stuff that's going out the renal. Very different. Okay? Okay. Not do you love it, but can you get it? Okay? So I will give you guys a quiz on Tuesday, just because I know you need to study that. Right? In between eating some turkey, I mean, you're going to be spending a lot of time in the toilet anyway. You might as well study, right?
It'll be from where we left off before.
No, I think I'm going to give you a cardiovascular and urinary quiz because I think it'll do better for your studying if I combine the two of them. Not respiratory, which we're going to start today, but
From where we left off before into the heart and
I don't remember where we left off.
Right by that table. Just above the table.
No, I'll do the whole thing. All cardiovascular system. And urinary. You'll be prepared for your test. Your test is coming next Thursday. If I do that, you will study most of the material for your test before next Tuesday. And I know.
That's enough, basically.
What?
Both of these tests are enough.
But not respiratory. Okay, so let's finish urinary system. This stuff, we just did all the hard stuff. Okay? And by the way, if you sit and make a million pictures about what's moved where, you will get this, especially if you study today. If you study today after I put up the notes, the second time you hear it, it will make a lot more sense, I promise. Did anybody sit through 2 sets of lectures today? Not a single person? Oh, motivation falls at the end of the semester, huh? Some people sit through 2 lectures. He's not even in this one.
Yeah, he's not.
Yeah, I'm about people who sit through 2 lectures.
Sometimes you do. You didn't today, though. You wish you did? Okay. All right. But we're done with the hard stuff. This is the easy stuff on urinary system, and we're not going to do anything really difficult on respiratory today. Nothing difficult. So final volume of urine. How much do you pee per day? Not you personally, just people in general. Around a liter. You must drink a lot of water. Drink a lot of water. I don't drink enough water at all. No, everybody has approximately the same size bladder. It's your micturition response. Around 1,000 mils to 1,800, so 1 to 2 liters-ish per day is how much you pee. And it's affected by, directly affected by your blood pressure, and that should make sense because blood pressure increases GFR, which increases filtration. If your blood pressure is higher, you tend to pee a little bit more, and if your blood pressure is low, then you'll trigger renin, angiotensin, aldosterone to make you retain at least enough, right? Okay, but then there's also the physiology that you have known since you were a kid, and that is that if you drink a lot, you pee a lot. But I want you to understand the physiological steps in between that. That's all, and it's really not hard at all. So if you drink a lot of water, here's what's happening. The water concentration in your blood increases, becomes slightly hypotonic, right? Detected in your brain, ADH is secreted, okay? ADH secretion is inhibited. Sorry about that. ADH secretion is inhibited because it says we have plenty of water. And when ADH secretion is inhibited, 2 things happen. You are not thirsty, and you let go a whole bunch of that DCT water, right? That makes sense? You let go a whole bunch of that DCT water. It doesn't do anything to sodium ion reabsorption because it's not impacting your aldosterone, right? Does that make sense? Okay, so you can lose sodium. You can lose sodium at the DCT without losing water, right? You can also lose water at the DCT without losing sodium because it will follow some of the other ions, just not as strongly, other ions. Okay, if you are dehydrated, however, what happens is the water concentration of your blood plasma is too concentrated, too many ions in it, right? Too much stuff in it. Detected slight hypertonicity, right, in your brain. And then your brain says, hey, we need more water. And the way that it communicates that is to release ADH. And then ADH tells your distal convoluted tubule and your collecting duct to do water reabsorption, right? And then, so we know this. If you don't drink very much, you don't pee very much. But this is also the reason. If you don't drink very much, you release ADH, which causes water reabsorption, and you don't pee very much. That's the relationship. It will also make you thirsty. ADH makes you thirsty. Okay? So a couple other things that impact urine volume, temperature. This one's kind of interesting. When you're exposed to high temperature, a couple of things happen. First of all, you do cutaneous vasodilation, right, to cool yourself down. That alone will drop your blood pressure, right, because you're like sending it through more vessels, right, especially like a superficial vessel. So that drops your blood pressure, which decreases GFR a little bit. But in addition, you will also activate the sweat response. And when you lose fluid this way, it changes the tonicity of your blood, so you don't need to lose it that way, right? That makes sense? So as the fluid in the body decreases, ADH and aldosterone secretion increase, right? Because you're sweating out both salt and water. And the regulated reabsorption of water at the DCT will continue. So if you sweat a lot, you won't pee as much. That's true. Okay, so your urine volume decreases and it's stinky and concentrated. Okay, but when you're exposed to low temperature, and this is the one I find really irritating, like when you're camping. Did we talk about camping before? Camping in high temperatures? Okay, so when you're camping and it's the middle of the night and it's just freaking cold, just cold, you have to pee. It's completely annoying. It's the worst thing ever. And here's why. Because when you are really cold, you do peripheral vasoconstriction to keep all that warm blood near the parts that are important, right? From here to here. And what does that do to the pressure in your abdominal pelvic cavity? It increases the blood pressure in your abdominal pelvic cavity and you increase filtration. And so you have to pee when it's cold. It's terrible, okay? Yeah, that's why I always take my husband's shoes in the middle of the night when we're camping. They're easy to get on, and if I'm going to pee on somebody's shoes, it's not going to be mine. His shoes, he's like size 13, you know. Last thing you want to do is try to struggle to get your damn boots on. No, don't tell him. You would tell him, wouldn't you? Yeah. You never meet him. My husband like never comes up here. He's seen me lecture like twice, and like we've known each other for 18 years, and he's still never seen a cadaver. Never seen a cadaver. Huh? He totally is. That stuff's interesting, man. But the cadavers are fascinating. I'm going to show him all your pictures, at least make him look at the pictures. Richard's taking some amazing photos for cadavers as his project. Not like we have permission, body donor program. No, he's doing them for future anatomy students, and I'm going to label them all. It's going to be beautiful. Okay, diuretics. Sorry, we just like got lucky enough to have a professional photographer who also wanted to be a lab assistant. It's been a very, very nice semester. Those guys are doing an amazing dissection too. They're getting photos too. Okay. So diuretics can also change your urine volume, right? A diuretic is something that makes you pee a lot. And there's several different kinds of diuretics. And in order to like understand the diuretics, you just have to understand this stuff. So some diuretics work on the 65% PCT, reabsorption of sodium and water. Some of them work on the 35% reabsorption of sodium and water, and some of them really just work on filtration. So let's look at what they do. So some diuretics inhibit the 65% PCT, reabsorption of sodium and water. Now, I told you can't regulate that, but they did create some chemicals that could regulate it. You don't have any inherent mechanisms to regulate that 65%, but there are, like Lasix will work on that. So here's what they do. They inhibit the 65% reabsorption at the DCT of sodium and water. But the problem with that is that means that you deliver that much more, did I say PCT reabsorption. If I said DCT, I didn't mean that. So they inhibit the 65% that's supposed to happen here, but then you deliver way more to the DCT of water and sodium. You got it? And so then, of course, it tries to get rid of as much as possible, but the problem with trying to get rid of as much sodium and water as possible is it's going to cost you aldosterone, right? So if you try to do DCT reabsorption of sodium and water all the way up to the 35%, every single time you do that, it's going to cost you some potassium or some H+. So these are really, really effective diuretics. And my student, Karen, who's in the last class, who's like a paramedic captain, she said that these are amazing. Like if you have congestive heart failure and like the person can't breathe, you give Lasix or something and it immediately drops the blood pressure so that they can breathe. So it's like within like 10 minutes. You're going to have to pee all over yourself when you use these. But the problem is that it causes a dangerous loss of potassium because it forces this to happen. Does that make sense? Dangerous loss of potassium. So when you are on these type of diuretics, a lot of times you're also on a potassium drip, right? To replace the potassium that's caused with this. So it's kind of counterintuitive because it affects here, right? But then you try to compensate with the distal convoluted tubule. That's the problem, right? Okay. So these hydrochlorothiazide and Lasix are two examples of those. Okay. Some diuretics, however, work directly on the DCT, and they interfere with aldosterone. And they're not going to be as effective because they work on 35% instead of 65%, right? But they're also not as dangerous because what they do is they interfere with aldosterone, and if you interfere with aldosterone, you're not going to have potassium loss, right? So they inhibit the regulated reabsorption of sodium, and so you lose some extra sodium and water up to 35%, right? but potassium ions are retained. They're not as effective, but they are used as maintenance medication. And one of them is spironolactone. And then alcohol. Alcohol is a diuretic because it inhibits ADH release. Alcohol inhibits ADH. Since it inhibits ADH, it is an anti-diuretic, right? And it works on that 35% water reabsorption. It doesn't directly impact sodium reabsorption. It works on that 35% water reabsorption. Okay? And then we know that coffee is a diuretic as well, right? Caffeine is a diuretic, but for a super simple reason. Caffeine just slightly tweaks your blood pressure. And as it slightly tweaks your blood pressure, it doesn't do anything to those two, but it increases filtration. That makes sense? Okay. And then there are what we call the osmotic diuretics, and the osmotic diuretics are the ones that you can buy over the counter. I don't know if you can buy. I know you can't buy Lasix or anything over the counter, but I don't know if you can buy those. But the osmotic diuretics would be like in those pills that they sell for bloating, for like premenstrual bloating. A lot of times it's in Midol along with the pain reliever, Premicin, those kinds of things. Here's what it does. It's a chemical which we know will be filtered out but has no reabsorption mechanism. And so as it goes through the tube, it exerts an osmotic effect on the tube, right? And ends up pulling water, kind of like eating too much sugar does, right? Does that make sense? So those are called osmotic diuretics. They get filtered out and there isn't a mechanism to bring them back in. So they suck water into the tube. Everybody okay with those? Okay. All right. And then the last thing in this set of notes is just to talk about renal calculi, which is kidney stones. And kidney stones are little beasties. Here's some kidney stone pictures. Look at those buggers. Agony, pain, misery. I would think that this one, if misery is the worst, that's got to be that one. That one's super pointy. So here's where they form usually. They form in the minor or major calyces of your kidneys, sometimes in the renal pelvis, and then they have to be expelled all the way through your slightly stretchy, but not that stretchy ureters, right? Ow, 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 ow. And then into your urinary bladder, which is probably fine because it's big enough that they might not cause problems as they're in the urinary bladder. Then they have to go through your urethra, which is exactly the time that you will wish that you were a girl. Because the urethra in girls is only 4 centimeters long, about 1.5 inches. But in men, it goes all the way from the bottom of the bladder down all the way through the penis. And so in an average man, that's 8 inches. I'm not saying the penis is 8 inches. Was not born yesterday, okay? But all the way from the inside to the outside. Sorry. Promised I was going to be good. They exist. Okay.
It's okay.
They are your children, aren't they? Okay. 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 So renal calculi. They can break them up with like lasers and sonar. Isn't that what they use? But then you just have to pass a whole bunch of little pieces instead of a big piece. Anybody in here ever had a kidney stone? No kidney stones? Oh, just one? Terrible, huh?
I had a lot. I passed a couple naturally. They were like, here's some oxycodone, go home. And then I had, I didn't do the lithotripsy. Instead, they used like a little tiny claw thing to go in and take it out. And they pulled out 128 and gave it to me in a test tube.
Why did you have 128?
They don't know.
Oh my gosh. You need to make a horror story about that. Oh my gosh. Oh. I'm having sympathy pains. Okay, so how do you get kidney stones? I don't know how she got 128. But if your urine is super, super concentrated, you're more likely to get them. Because then you have all of these concentrated ions which will crystallize, especially your cations will crystallize. Calcium and magnesium are the primary components of those. Calcium and magnesium solidify into insoluble stones. And in the conditions leading to urine formation, decrease in fluid intake resulting in very, very concentrated urine. Abnormally acid or alkaline urine make it more likely for the kidney stones to form. Or ingestion of excessive mineral salts can do it.
Do you think drinking a lot of hard water would increase that? Like, from out of your process?
What are the ions in hard water? What? I can't remember what minerals are in hard water versus salt water.
I think it's got a lot of calcium.
I don't remember. My water's super hard up in the avenues, but is it water softeners that increase the likelihood?
Water softener, because you put all the minerals and salts into the water softener, and then that softens the hard water. But if you drink that, that's a lot of salt.
Huh. I don't remember which ones. I don't know the chemistry well enough, but I could check into that pretty easily. Overactivity of parathyroid glands because you get too much calcium in your bloodstream, right? And phosphate ions. But the big one, and I put a question mark by it, but I should take it away now, but that we actually now know that soda consumption dramatically increases your risk of kidney stones, especially diet sodas. Diet sodas are saltier than regular sodas. And in addition to increasing the salt concentration, they also screw up the pH, which will make kidney stones likely. Did they tell you not drink sodas when you got that many kidney stones?
I got conflicted information. Somebody told me not to, and then somebody said that there was a cure if you drank like a 12 pack of Coke, it would pass. So I don't know.
But a full tank of water.
12 pack of Coke. Was this your ex-husband?
I think they said like the phosphorus or something, or the carbonic acid in the soda would break it down. I don't know.
No. Sodas are terrible. I mean, urologists agree on this one. Go ahead.
So my mother was recently diagnosed with hyperoxaluriasis,
Okay.
which your kidney, I guess, or not your kidney, your liver makes too much oxalate, which when it goes
Mhm.
to the kidney, it collects with calcium, and she was told not to drink any soda.
Not to drink any sodas at all. Yeah.
And she also can't eat like spinach and like a bunch of weird things that
Mm.
make your liver produce oxalates.
Wow.
But in the last year, she's had 8 of those sonar surgeries to break up
Oh.
kidney stones.
But you still have to pass them. It
She
just
still has to pass them, yeah.
was not nice. I just do want to tell you guys a couple things about diet sodas since we're here. Diet sodas are worse than regular sodas for this. And in addition, I don't know if I told you that, guys. There was a study that just came out that I found really interesting that diet sodas, they used to say that it was okay for diabetics to drink diet sodas, but now they say, nope, not even supposed to be drinking diet sodas. So 2 studies over the last 5 years. One of them shows that people who drink diet sodas usually weigh more than people who drink sodas. Yes. Mm-hmm. Yeah, I know. It's like drink a freaking Coke if you want a Coke. Like, don't drink 7, but drink 1, and don't drink a Diet Coke. So they usually weigh more. And in addition, apparently your body can't tell the difference initially and causes an insulin release, even with drinking a diet soda. So your body, like, it's not good for diabetics. They actually cause insulin release. It's not as much as drinking real sugar, but it is also an insulin release without sugar to bring it down, right? Like the sugar response. So you have, it's about 30% of the insulin release as drinking a real soda, but then they drink a lot more of them because they think they don't have calories, and they don't have calories, but they're terrible. They're like the work of the devil, totally worse than regular sodas. Drinking Mexican Coke, it's got real cane sugar in it. Those things are delicious. Huh?
Some product in there that starts with
Aspartame?
yeah.
It is, yeah, it's a lab-created artificial sweetener that doesn't have calories.
Stronger than gluten and sugar.
Yeah, it's really, really strong.
Drop is like equal
Yeah.
to 7.
Okay, so what should you do? Don't drink sodas. Keep trying to tell myself. I stopped drinking sodas like,
Yesterday.
no. I did. My daughter, like my 12-year-old, she stopped drinking sodas, and so like I was trying to support her, and I stopped drinking them. I didn't ever drink very many of them, but they're really good mixers for cocktails, which is great. So, yeah.
You can't count it.
You have to count it. So I stopped drinking them, and I've had like one over about the last 3 months, I think. But I miss them. I will like look at a Coke and be like, oh. I didn't never drink them that much, but it's like whatever. Anyway, drink lots of fluid, especially at bedtime. Sounds really irritating, but I think peeing in the middle of the night is less irritating than a kidney stone. I'm not sure. But and the problem with nighttime is that you're not going to pee for a while, so whatever concentrated stuff you have in there will sit in your kidneys for a little while, and they're more likely to crystallize. And limit intakes of certain salts like oxalate and urate, but don't limit intake of calcium because nervous system, blood clotting, that kind of stuff. Cool. I don't want to do dialysis review because I already taught you that once. So we're going to go to respiratory system. Sorry for talking about penises with your girls in the room. I'm trying to figure out what to do because my son has to come to work with me tomorrow, and I'm teaching anatomy, and I am on the male reproductive system, including the phases of the male sexual response, ejaculation. 7. Huh? I got him. He's got an iPad, and I'm going to get him a new game tomorrow. And I don't really care about him knowing those, but I don't really want to be answering those questions during Thanksgiving dinner.
Yeah.
With my incredibly, incredibly conservative mother-in-law who left last Thanksgiving dinner because she was pissed off because we were talking about Mitt Romney. And still every single time, she's so conservative, every single time she talks about Obama, she calls him Obummer. And I'm like, that is the oldest damn joke. Could you please come up with another one? If you're going to be irritating, at least be funny. That's what I'm trying to say. Obummer? Really? Again? That's what she does. Okay, so if you didn't, the anatomy of the respiratory system is not super complicated. The only thing that's really important that you need to know is, as far as respiratory anatomy, the alveoli are the microscopic little balls. They're little bubbles that you get to as you get to the end of the lungs, so from the inside. And they are the reason that your lungs are so dense, because your lungs are really like one of those expensive Williams-Sonoma sponges, right, that has teeny tiny little holes in it, not the cheap one that you can get at the grocery store. So they have teeny tiny little holes in them. So tremendous surface area. And each individual one of these alveoli is wrapped with a capillary. And so there's capillaries all the way around them. And that makes very, very thin, lots of surface area, really good for gas exchange. You don't have to worry about gas exchange if you can just get air to the right place, because oxygen is lipid soluble and it will move straight down from the high concentration that it is in the air into the low concentration that it is in your pulmonary blood that's going by, right? And carbon dioxide does the opposite. So you don't really have to worry about exchange. You don't have to do any of these fancy mechanisms. Transporters and carriers, just get it to the right place and it will move. So the anatomy is not super difficult. Okay, a little bit about the terminology associated with respiration. Okay, so there are some steps in respiration and things can go wrong at any place. The first thing is called ventilation. And ventilation is simply breathing. It's breathing in and breathing out. That's not the same as respiration. Ventilation is composed of inspiration, which is breathing in, right? And expiration, which is breathing out, or inhalation and exhalation, okay? But then, after you get the air in, you have to do respiration. Respiration is the gas exchange. Is that okay? Respiration is gas exchange, and we do gas exchange to 2, arguably 3 places. The first place that we do gas exchange is between the alveoli, which is where the air came in, and the pulmonary blood and the capillaries, right? That's called external respiration. It's closest to the outside. Does that make sense? So, of course, oxygen is going to move in and carbon dioxide is going to move out. That's external respiration, okay? And then you have to send it back to the heart, right? And do circulation. And then circulation, send it to systemic capillary beds, like the brain or the liver or wherever. And we get to systemic capillary beds, we do respiration again. This time we call it internal respiration. And the internal respiration is generally between the systemic capillary bed and the tissue around it. So I'm going to move oxygen into the tissue around it and carbon dioxide from the tissue in. And all of that is serving cellular respiration. Yes? And so in each cell, you're gobbling up oxygen and generating carbon dioxide. Cellular respiration, by the way, is what generates the concentration gradient for all of this, because you are constantly using up oxygen and generating carbon dioxide. Is that okay? So that's what we will mean when we talk about these. So the first thing that we're going to talk about here is ventilation, which is breathing, and lung mechanics. It's not hard. The process of inspiration or inhalation is simply simple physics. I will explain to you why the lungs are stuck to the thoracic wall in a little bit, but let me tell you that the lungs are stuck to the thoracic wall, kind of like 2 slides are stuck together when you get them wet. And then try to pull them apart. There's negative pressure in there, and it keeps the lungs stuck to the thoracic wall. So whatever the thoracic wall does, the lungs are stretchy and they follow it, as long as you don't puncture the cavity. If you puncture the cavity, then the lung will collapse, but we're not going to do that yet. So inspiration is simply increasing the size of this cavity. It's the thoracic cavity. And when you increase the size of a cavity, you decrease the pressure in a cavity. Does that make sense? So if I take a cavity and I stretch it, then the pressure goes lower. So things are less crowded in there, right? Or if I take a cavity and I squish it, the pressure goes higher, right? All I need to do is change the pressure so that either goes above or below atmospheric pressure. Atmospheric pressure is relatively constant. It's around 760 millimeters of mercury. It changes as you change elevation, but we're not going to change elevation between a breath, right? Make sense? So what will happen is if I squish the cavity so that the pressure is higher than atmospheric pressure, then air moves like fluids do from high pressure to low pressure, right? If I stretch the cavity so that the pressure is lower than atmospheric pressure, right, then air moves in, right? So let's talk about how the musculature, the anatomy, generates those pressure changes for inhalation. It's easy. With inhalation, what happens is the size of the thoracic cavity increases primarily because of contraction of two sets of muscles. The first one is the diaphragm, which when you are not breathing in, is shaped like this. When I breathe in, it pushes down, okay? That increases the size of the thoracic cavity, correct? And decreases the pressure. Simultaneously, you will also contract your external intercostal muscles, yes, and they will actually squish the ribs together and pull them up. So those two things combined will increase the size and therefore decrease the pressure in the thoracic cavity. As long as you are dealing with a relatively constant atmospheric pressure, you drop below it, air moves in, right? Do you have to actively suck it in? You don't. You can if you really wanted to, but you don't have to. It's passive, okay? It's primarily that air will move in when you contract these muscles. Does that make sense? Okay? So the process of inhalation is you just stimulate the diaphragm muscles, the muscles contract, the chest wall expands, it pulls on this pressure that we'll talk about, the fluid in there, and then eventually, basically, you will get air moving in. The air will move in. So the walls of the lungs will stick with the thoracic cavity as long as you have a negative pressure here, and we'll talk about how that happens in a little bit. So basically, what we are going to do with respiratory system is, so this one shows the muscles. If you guys remember, the diaphragm is bell-shaped, and then the external intercostal muscles are out here, and they're involved in inspiration. The internal intercostals will be involved in expiration. We'll talk about that in just a second. At least sometimes they're involved in expiration. There's a figure that I want to show you. Okay. I'll bring you those pressures in just a second. Okay, so how do you cause expiration or exhalation? Primarily, it's just a relaxation. So when you relax the diaphragm, it goes back up here, right? And when you relax the external intercostal muscles, the ribs push down, right? Fall back down, basically. And so that will generally be enough to increase the pressure in the thoracic cavity and in the lungs above atmospheric pressure, and then air will move out. Now, you can do forced expiration, but that's not involved in what we call tidal breathing. Tidal breathing is the regular breathing that we'll do. But if, for instance, you are talking and breathing at the same time, a lot of times you're going to have to push air out, or if you're blowing out a birthday candle, then that will be forced expiration, or when you're working out, you will do forced expiration as well. It's just getting the air out more effectively. Forced expiration is when you, in addition to relaxing the diaphragm and relaxing the external intercostals, you will contract the internal intercostals. And when you contract the internal intercostals, you'll pull the ribs closer to each other, right? And squish out the air, usually at the same time. And you can feel yourself doing that. If you do forced expiration like you're blowing out a birthday candle, you can feel your ribs pushing together, and you can feel your abs pushing up on the diaphragm. So you can feel, it's kind of interesting. You can feel your abs like pushing up. That's forced expiration, but you don't do that all the time. Do it. Aren't you curious? Huh? You don't have too much there.
I can't feel anything.
You can feel it. So is that okay? So that's generally what you're doing, is you are changing what we call the alveolar pressure, the pressure inside the lungs with reference to the atmospheric pressure. So now what we get is to talking about airflow. And unlike flow of the cardiovascular system, which we wanted to be unidirectional, right? We want to make sure it just goes one direction. With flow of air in and out, we want it to be 2 directions, right? And so what we're going to do is we're going to vary the size of the container above and below atmospheric pressure so that air will move in and out, okay? And so you're going to have a really similar equation to the one that we looked at with blood flow. Remember, blood flow was F equals delta P over R, right? Okay. Flow of air moves from high pressure to low pressure. It's also delta P over R, but the delta P is always with reference to atmospheric pressure, which is relatively constant. So it's P sub atmospheric pressure. It's comparing atmospheric to alveolar pressure. Is that okay? So if the atmospheric pressure is bigger than the alveolar pressure, then you're going to breathe in, right? And if the alveolar pressure is bigger than the atmospheric pressure, then it's going to move out, right? And the resistance will be things like size of the tube, is it gunked up with mucus, you know, those kinds of things. And also the stretchiness of the lungs as well. Conceptually, you kind of understand? Okay, so it's the changes in pressure that are going to be responsible for ventilation. So the flow of air into and out of the lungs is governed by 3 principles. And we will get to those next time, but let me just tell you that there's this simple physics called Boyle's law. How many of you guys have had physics? Okay, so Boyle's law is one of the parts of physics that's not that bad, because Boyle's law simply says if you take a container that's closed and you squish it, the pressure increases, and if you stretch it, the pressure decreases, right? But that's okay, right? That's a really simple physics law. So basically this air moving in and out depends on Boyle's law, and then changing the container will depend on the muscles involved in respiration. Okay? Good? Okay. I will see you guys on Tuesday. We have a quiz on Tuesday over cardiovascular and urinary, not respiratory. And I may, if I look at this and it seems like too much to finish on Tuesday, I may post a short lecture to get you through the easy parts before Tuesday. You don't have to watch it until after Tuesday if you don't want to. I don't care. But just between Tuesday and Thursday might be a little too late for you to study. You know what I mean? Respiratory? Huh? After I get some food. I'll be there in about 10 minutes. Yep.
What room again?
SI 317.